Swayam Prabha. Digital India. Educated India.
Welcome friends to this NPTEL online certification course of environmental soil chemistry, and we are currently going through our week 4 of lectures, and our topic in this week 4 is soil solution, solid phase equilibria and sorption in soils. And today will be today will be the third lecture of this week. And but before discussing the materials in the third lecture, I just want to go for a quick recap of whatever we have discussed so far. So so far we have covered the measurement of soil solution, and then we have covered the speciation of the soil solution. Then we have covered the ionic activity and activity coefficients, dissolution and solubility processes, surface complexes, and so basically we have covered up to dissolution and solubility process, and we have covered up to the stability diagram. And so just to give you a quick recap of whatever we have covered so far, we have discussed about the soil solution and what is, we have talked about briefly about the inner and outer sphere complexes, and then we have discussed about the dynamic equilibria reaction in soil, and in other words how the free ions as well as the complex forms of ions can move from soil solution to different pools, and when all these movements are reversible, so they also can come back to the soil solution. How this process occurs, there is we have seen that there are total 12 processes through which this ion can move from soil solution to different pools and then come back to the soil solution again. So then we have talked about the intensity factor and capacity factor, and we have covered the main types of technique which we use for extracting the soil solution. Remember that this is the displacement techniques. We have talked about the centrifugation and saturation pasts. So this is the column displacement we have talked about in our previous lectures. Then we have talked about how centrifugation can remove the soil solution for subsequent measurement, and what are the other aspects of centrifugation we have talked about. And then we have talked about the saturation paste or saturation extract, and how we can extract that soil solution to measure the ionic concentration in the saturated extract. Obviously, we have also talked about the speciation of the soil solution, which is very important. We have talked about the hydrolysis, how hydrolysis process occurs, and how these general complexation reaction between a hydrated metal and ligand, and how it to form an outer sphere complex. We have discussed this reaction, and then we have talked about in details about the speciation. That means a mass balance equation for total concentration of metal ions in the soil solution can be given as a as a summation of a concentration of the free hydrated metal ion species as well as concentration of metal ion associated with the remaining metal ligand complexes. And then we have talked about some important stability constants like conditional stability constant, and then thermodynamic equilibrium constant, and what are the properties of thermodynamic equilibrium constant. We have shown one reaction. From there we have talked about the thermodynamic equilibrium constant, and then we establish a relationship between the we establish a relationship between the activity and concentration with the help of activity coefficient. for a particular species, and using that we have established the relationship between the conditional equilibrium constant or conditional stability constant and thermodynamic equilibrium constant. And from there we have seen that thermodynamic equilibrium constant is related to the conditional equilibrium constant, where conditional equilibrium constant multiply by ionic activity ratios, ionic activity coefficients, they when you multiply the conditional probability conditional stability constant with the ionic activity ratio, then we can get the thermodynamic equilibrium constant. Then we have discussed one numerical problem where we can calculate the concentration of different calcium species present in the soil solution from a basic soils, and then we have seen how we can do that. I have discussed in details, so I am not going through in details again. So from there, so we have already covered these things. Then we have talked about the ion activity and the activity coefficients, how we can calculate the ionic activity, what is the formula of the ionic activity, how we can calculate the ionic strength, and how these ionic strength of different monovalent and divalent cations changes and trivalent cation changes, and depending upon the concentration, and when the concentration is higher, then how it follows the Davis equation. And then we have shown you the calculation of shown the sample problems for measurement of I by for different compounds like potassium nitrate as well as potassium sulfate. And also we have identified, I have shown you how to calculate the activity coefficient for a for cadmium ions at a particular temperature and with a particular ionic strength. So then we have talked about the dissolution and solubility. Remember, the dissolution and solubility depends on the basically controls the weathering, soil formation and contaminant mobility, and for different soil like calcareous minerals like gypsum dissolve relatively rapidly and congruently, and what is the incongruent reaction we have talked. Then we have talked about the dissolution of the silicate minerals, and from there we have shown you how to use the solubility, how to calculate the thermodynamic dissolution constant, which is denoted by this K0 Ds for a particular reaction when this gibbsite is reacting with the proton to produce the aluminum ion as well as water, how this thermodynamic dissolution constant can be calculated. And based on this thermodynamic dissolution constant, how we can calculate the thermodynamic solubility product constant, and what is the relation between the ion activity product and solubility ion activity product and the solubility product constant, and how it changes and how it governs the solubility or precipitation of different mineral phases. And then we have talked about the stability diagram. The stability diagram gives us the answer for whether a solid phase control the concentration of an element in the soil solution, and if it does, what is the solid is. And then we have talked about this standard free energy formation, how this standard free energy of formation can be used to calculate the free energy accompanying the reaction. And from there, considering the reaction of gibbsite with the proton, how we can calculate this delta Z0 R, and from there how we can get the stability diagram. Remember, the stability diagram can be calculated based on these two, that is log of aluminum for, and as well as log of aluminum is in the y axis, whereas pH in the x axis. And then I showed you how this stability diagram can be made for different aluminum and iron oxides or hydroxides, and how we can differentiate their solubility based on this solubility stability diagram. So, similar diagram can be done in case of, I showed you in case of kaolinite, has the dissolution reaction of this, where the kaolinite can be reacted with the 6 protons to produce the aluminum and silicic acid and water, and this associated dissolution constant can be calculated as 5.45, and from there we can get this reaction, simplified reaction, as you can see here, log aluminum plus 3 pH equal to 2.73 minus log of H4SiO4. This log of H4SiO4, also known as the PH4SiO4, or it is the negative logarithm of PH4SiO4, is basically negative logarithm of silicic acid concentration. So, if we plot the logarithm of silicic acid and the logarithm of Al3 plus pH in the y axis and logarithm of silicic acid in the x axis, we can see the stability of different clay minerals. For example, the vertical lines, as you can see here, they are basically producing the silica quartz, because they are straight line, because in their structure there is no aluminum, and their dissolution reaction is independent of this aluminum. So, they are basically the straight line. However, the stability diagram are very useful predicting the other stable solid phases. For example, 2:1 minerals like montmorillonite are stable only when the concentration of silicic acid in solution is controlled by solid phases more soluble than quartz. And you can see here that here, as the pH decreases, from 1110 to 9, and this condition, that is log of aluminum plus 3 pH, as it decreases, we are getting from illite to montmorillonite to ultimately kaolinite. If you remember the stability of different clay minerals which we have discussed in our week 2 of lectures, obviously the illite and montmorillonite are the earlier stages of weathering, whether at the advanced stages of weathering we get this kaolinite. And one important observation is that this is consistent, as kaolinite is the most dominant phyllosilicate mineral observed in acid soil. That means, more acidic the soil, you will see the dominance of kaolinite that receives a substantial amount of rainfall. So, this kaolinite is present in the soils which goes through extensive leaching or substantial amount of rainfall. Under more extreme leaching condition, you can see under more extreme leaching condition, that means when the H4SiO4 is less than 5.3, that means when it is less than 5.3, that means in this region, obviously you will see that only this gibbsite is more stable than that of kaolinite. So, as the silicic acid concentration is going down and pH is going down, then we can see the predominance of gibbsite instead of kaolinite. So, this shows that this is the basis through which we can develop the presence of different clay minerals at different stages of weathering. Whether it is an advanced level of weathering, when there is a extensive leaching, we will see kaolinite. In the earlier stages of weathering, we will see illite, and the intermediate stages of weathering, we will see the montmorillonite. Now, we will go to the adsorption. Now, adsorption can be defined as the accumulation of the substance, accumulation of a substance or material at an interface between the solid surface and the bathing solution. Remember that adsorption affects the electrostatic properties, for example, coagulation and setting of suspended particles and colloids. Now, both physical and chemical forces are involved in adsorption of solutes from solution. Remember, adsorption is a surface phenomena, whether absorption absorption is an internal phenomena, whether adsorption is a surface phenomena, and it can be governed through both physical forces as well as chemical forces. In the physical forces, van der Waals forces and electrostatic outer sphere complexes are important. However, in case of chemical forces, ligand exchange mechanism, covalent bonding and hydrogen bonding are important. As you can see in this picture, this is a physical adsorption, and physical absorption basically occurs through these either physical processes or chemical processes. However, the chemical adsorption the physical adsorption, you can see that it basically goes mediated through either van der Waals forces or electrostatic outer sphere complexes. As you can see, it is an electrostatic outer sphere complexes. Outer sphere complexes where there is a presence of internal water molecule. However, in case of chemical adsorption, you can see either formation of covalent bonding or hydrogen bonding or ligand exchange reaction. So, although they are adsorption, but depending on the nature of adsorption, we can differentiate either it is a physical type of adsorption or chemical type of adsorption. Now, surface complexes. What are the surface complexes? When the interaction of a surface functional groups with an ion or molecule present in the soil solution creates a stable molecular entity, it is called a surface complex, and the overall reaction is referred to as a surface complexation. Remember, in the surface complexes can be, there are two types of surface complexes. We have already covered them briefly. They are outer sphere complexes and inner sphere complexes. Now, these shows a more clear picture of outer sphere complexes and inner sphere complexes. The first picture shows the inner sphere complex, where the potassium is it is placed in the interlayer space of vermiculite. It is producing a lock structure. Now, you can see in this potassium, this is a inner surface complex. However, there is an outer surface complex can be found in case of montmorillonite, whereas the calcium is present surrounded by water molecules. So, these are two different complexes. One is the inner sphere complexes, and in case of outer sphere complex. In case of inner sphere complex, you will not see there is an intermediate water molecule. However, in case this is an inner sphere complex, there is no intermediate water molecule. However, there is an outer sphere complex where there are outer intermediate water molecule. So, these are the examples of inner sphere complexes and outer sphere complexes formed between metal cations and siloxane ditrigonal cavities on 2:1 type of clay mineral. We will see these cavities. Now, talking about the outer sphere complexes, we all know that if a water molecule is present between the surface functional groups and the bound ion of the molecule, the surface complex is termed as outer sphere. Now, remember, in this outer sphere complex, it involves electrostatic Coulombic interactions. Now, these outer sphere complexes are weak as compared to the inner sphere complexes, and complexation is rapid process that is reversible, and binding is basically covalent or ionic binding. Now, adsorption occurs only on surface of opposite charges to the adsorbate. Obviously, this type of adsorption can occur in between the opposite charges. Now, I am showing you one inner sphere surface complex. Now, inner sphere surface complex, if there is no water molecule present between the ion and molecule and the surface functional groups to which it is bound, then it is known as the inner sphere complex. Now, remember, the inner sphere complex can be monodentate. By monodentate, it means that the metal is bounded to only one oxygen, and can be bidentate, where the metal is bounded to 2 oxygen, and can be mononuclear and bionuclear, slower, and also they are not reversible. So, inner sphere complexes are not reversible, they are slower as compared to the outer sphere complex. They can form either monodentate complex or bidentate complex. So, you can see here, this is a schematic illustration of the surface structure of arsenic. You can see here, it is a monodentate complex, and in the monodentate complex, this arsenic is basically bounded with this iron atom with a single oxygen. So, this is a monodentate complex. In case of bidentate complex, you can see arsenic is bounded to 2 oxygen, and this is a bidentate complex. However, this is a mononuclear. However, this is also binuclear bidentate complex, where arsenic is linked with 2 oxygen, which is basically coming from 2 iron atom, which is also in terms of linked with the 2 different iron atoms. So, it is bidentate binuclear complex. Now, it is a monodentate complex. You can see chromium, which is bounded to the single oxygen, which is also in terms bounded with the iron to form an inner sphere complex. So, it is a monodentate complex. This is a bidentate complex. You can see it is a mononuclear bidentate complex for chromium, and also this is a bidentate binuclear complex of chromium, where the chromium is attached to 2 oxygen, which are in turn attached to 2 different iron atoms. So, this is the example of different types of inner sphere surface complexes. Now, apart from these monodentate and bidentate complexation, we can also define these surface complexes by assuming a polyhedral approach. Now, a polyhedral approach can be used to determine the molecular configuration of ion sorbed or mineral surfaces. Now, possible configuration include these 4 types of possible configuration. You can see one is a single corner. Monodentate mononuclear, we call it single corner monodentate mononuclear complex, in which a given octahedron shared only one oxygen with another octahedron. So, 2 octahedron are basically complex by sharing one oxygen. Second is a double corner bidentate binuclear complex, in which a given octahedron share 2 nearest oxygen with 2 different octahedra. So, you can see one octahedra sharing 2 nearest oxygen to 2 different octahedra. So, we call it double corner bidentate binuclear, because they are using they are attaching with the 2 oxygen and with the 2 different octahedrons. Third is an edge bidentate mononuclear complex, in which an octahedron shares 2 nearest oxygen with another octahedron. So, it is bidentate because it is sharing the 2 oxygen, and it is called the edge because it shares 2 nearest oxygen with another octahedron. And the fourth one is a phase tridentate mononuclear complex, in which an octahedron share 3 nearest 3 nearest neighbors with another octahedron. So, that is why it is called tridentate mononuclear. Now, it will give you more detailed picture of this polyhedral approach. You can see there is a finite number. Here we have seen an example of characteristic iron aluminum lead separation for Pb2 adsorbed to LO6 octahedra. Now, here we are assuming that these lead ions are having a trigonal pyramidal coordination geometries. You can see this is a trigonal pyramidal coordination geometry. So, here you can see corner sharing mononuclear monodentate. So, here this is a monodentate and this is a mononuclear, and also corner sharing bridging binuclear bidentate. You can see bridging bidentate and binuclear, since it is attaching with 2 LO6 octahedra. Third one is edge sharing mononuclear bidentate. So, here you can see it is sharing the edge, but it is bidentate because they are attached to 2 oxygen, and this is a mononuclear octahedra. And also phase sharing mononuclear tridentate. So, you can see it is linked with 3 oxygen 3 oxygen atoms, which are basically attached to 3 corners of a face of a octahedra. So, basically it shows the mononuclear tridentate octahedral coordination. So, apart from that, another thing is important. You can see that each linkage resulting in a characteristic lead aluminum distance. So, lead ions could adsorb either in monodentate, bidentate or tridentate fashion. We are clear from this polyhedral approach representation of the surface complexes. Now, remember that the sorption mechanism of metals and soil minerals are, they have, each and every metal can have multiple sorption mechanism on soil mineral. For example, you can see here in case of cadmium, when the sorbent is magnetite, we can see inner sphere complex. In case of it is L2O3, we are getting multinuclear complexes, and in case of silica, we can getting co-hydroxide precipitates, cobalt hydroxide precipitates, and in case of rutile, you can see small multinuclear complexes. In case of kaolinite, this cobalt produces cobalt aluminum hydroxide surface precipitates. This chromium, when the adsorbent is goethite hydroxyl ferric oxide, it produces inner sphere chromium hydroxide surface precipitate. In case of silica, it produces inner sphere monodentate. So, you can see depending on the sorbent and depending on the metal, it varies in its sorption mechanism. So, for each metal we can get multiple sorption mechanism for multiple different sorbents, and the sorption mechanisms are given here, and these sorption mechanisms have been well established by the research by the soil scientists. Now, let us consider another important thing, that is basic adsorption isotherms. Now, in the process of adsorption, adsorbate get adsorbed in the on the adsorbent. So, if we consider this adsorbent is basically soil in our case, and this adsorbate is basically the ions or metals which are present in the soil solution. Then in the adsorption process, these metal get adsorbed onto the soil surface, and the opposite reaction is known as desorption reaction, where those adsorbed metal ions can come back come back to the soil solution from the soil surface, from the clay surface. So, this is adsorption and desorption are opposite processes. So, you can see here it is represented by A plus B going to formation the AB complex and then reversible to A plus B again. Now, adsorption isotherm. What is called adsorption isotherm? The relation between the activity or equilibrium concentration of the adsorptive and the quantity of adsorbate on the surface at constant temperature is usually employed to describe adsorption. So, adsorption isotherm. Why it is called isotherm? Because this relationship is determined at a constant temperature. Iso means constant and therm means temperature. So, that is why it is known as isotherms, and we basically see the relation between the activity of the equilibrium concentration on the adsorptive. In other words, the concentration of a particular ion in the solution and their quantity in the adsorbate on the surface. So, basically the partition or the concentration of a particular metal ion in the soil solution as well as on the clay surface is basically denoted by adsorption isotherms and at a constant temperature. So, basically we use these adsorption isotherms to describe the adsorption process. Now, first solute adsorption isotherm was described by scientist Van Bemmelen in 1888, and in general the adsorption can be described by 4 general types of isotherm. One is called HS type, then L type, then H type and C type. Let us discuss them one by one. Now, first of all, this is a S type isotherm, and we can see if we put the concentration of a particular species in the soil solution, for example, and their concentration on the clay surface, concentration of their adsorb fraction in the clay surface. So, we will see that as the concentration in the soil solution increases, we will see this is an S type of curve. So, basically the slope initially increases with adsorptive concentration, or in other words concentration of a particular species in the solution, but eventually decreases and becomes 0 at vacant adsorbent sites are filled. So, obviously you can see initially it increases. So, initially it increases with adsorptive. So, initially it increases with adsorptive concentration. So, as we increase the adsorptive concentration, initially it increases, and then after a certain period of time you will see decreased and ultimately goes to 0 as the vacant adsorbent sites are filled. So, at low concentration the surface has a low affinity for the adsorptive, which increases at higher concentration. So, in other words, at low concentration, when we are seeing at low concentration, for example, in this area the surface has a low affinity for the adsorptive or the species, which increases as with the higher concentration. So, as we are going through, you can see the steep slope here. So, the concentration is getting high. So, this is called the S type isotherm. Now, another is called the L-shaped or Langmuir isotherm. Now, Langmuir isotherm is basically showing the decreasing slope as concentration increases, since vacant adsorption sites decreases as the adsorbent becomes covered. So, you can see here as the concentration is increasing, we are seeing there is a the slope is initially increasing and then it is decreasing. So, basically this decreasing slope as concentration increasing shows the vacant adsorption sites decreases as the adsorbent becomes covered. So, basically this Langmuir adsorption isotherm is basically for monolayer adsorption. We will see in we will see in details when we will discuss the Langmuir isothermal Langmuir equation in details. So, basically it is for monolayer adsorption, and as the adsorbent site is become covered, then obviously there will be less adsorption and ultimately the slope will be further decreased. So, basically this is basically explained by the high affinity of the adsorbent for the adsorptive at low concentration, which then decreases as concentration increases. So, this is the example of L-shaped Langmuir isotherm. The third one is called H-type or high affinity isotherm. So, basically this H-type or high affinity isotherm shows strong adsorptive interaction such as inner sphere complex. We know that inner sphere complex is a highly stable and there is a strong bond. So, here you can see with the smallest increase in adsorptive concentration, or in other words smallest increase in concentration of a particular ionic species, there is a steep increase of the adsorption, and this is showing the strong adsorptive interaction, and this is basically showing the high affinity of the inner sphere complexes. The fourth one is called the C-type isotherm, and it is basically showing the partitioning mechanism. Now, here one thing is clear, that adsorptive ions are partitioned between the interfacial phase and the bulk solution phase without any specific bonding between the adsorbent and adsorbate. So, as it is increasing the concentration of the adsorptive, we can see the adsorption is linearly increasing, and basically adsorptive ions are partitioned here in the interfacial phase and the bulk solution phase. We will see these in details while we will discuss the diffuse double layer. Okay. Now, adsorption experiments, how we do adsorption experiments. Now, in case of adsorption experiments they are basically carried out by equilibrating, that means shaking or stirring an adsorptive solution of a known composition and volume with a known amount of adsorbent. For example, in case of soil, we take a known amount of soil and then we shake or mix with a known volume of a particular solution containing a particular species of ions at a constant temperature and pressure for a period of time such that an equilibrium is attained. So, we basically stir or shake it for sufficient amount of time so that to attain an equilibrium. However, adsorption reaches at the equilibrium stage, the adsorption reaches a steady state or no longer changes after a period of time. So, at that time we can see that the equilibrium has been attained. Now, the pH and ionic strength are also controlled in most adsorption experiments. Now, after equilibrium is reached, then what we do? Then the adsorptive solution is separated from the adsorbent by either centrifugation, either by settling or filtering, and then analyzed. We know how to settle them, how to extract them. Either we can do it by centrifugation, either we can do it by saturation extract. So, different ways we can extract that soil solution, and then we measure the particular ion concentration, and from there we can calculate the adsorption or amount of adsorption. So, the degree of adsorption can be calculated by using the following mass balance equation. So, here C0 V0 minus CF VF by M. So, here Q equal to Q. So, Q is basically amount of adsorption. In other words, it is adsorbate per unit mass of adsorbent, or in other words, adsorbent means it is a concentration of a particular species per unit mass of soil in molecule per kg. Now, C0 and CF are basically initial and final adsorptive concentration or the solution concentration in mole per liter, and V0 and VF are basically initial and final adsorptive volumes in liter, and M basically represents the mass of the adsorbent in kilogram. So, this is how we can do different types of adsorption experiment. So, guys, you have learnt in details about different types of inner sphere complexes and outer sphere complexes and how they form the surface complexes. What is the mononuclear, and then what is the bionuclear, bidentate, mononuclear, bidentate, and then what is the tridentate coordination. Then we have seen the polyhedral approach for assuming these surface complexes, and then we have discussed about the four different types of adsorption isotherms, and I showed you how to do the adsorption experiment. So let us wrap up our lecture here. In the next lecture, we will be talking about specific adsorption isotherms, or Langmuir equations. We will be talking about Freundlich equations, and so on and so forth, and what is their implication, and also we will be discussing about the diffuse double layer. Thank you very much. Let us meet in our fourth lecture. Thank you.